Hello guys, welcome to Hall effect and Hall probe. Now this part is for the Hall probe which I'll explain later. Now first for the Hall effect. So what is Hall effect? Now when a current carrying conductor is placed in a magnetic field, it experiences some potential difference or some voltage and which is perpendicular to the plane of the current and magnetic field, which is known as Hall effect. Now so let's say we have a current in this direction and the electrons will flow in that direction. And let's say we have a applied magnetic field in that perpendicular to I, which will then produce a Hall effect or the Hall field, which is the electric field in downward direction. And here there will be some positive plates, positive parts on the upper surface and negative charge on the lower surface. Now this is a metal surface, and here the electrons will of course get attracted to the positive side, but here when you apply a magnetic field it deflects the electron downwards. That means at some point the Lorentz force will be equal to the electric force, meaning that the electrons will go undeflected. So Fe will be equals to Fl. So this is of course E H, because we're talking about Hall field, and the Lorentz force is BeV sine theta, but again theta is just the direction between magnetic field and current, which is 90 degrees. And you might say, well, this is a conductor, why don't we just use BIL? Well, can you use it? Of course, because here current you can write it as charge per unit time, so charge per time into length. And what is length per time? Well, that is just velocity. So ultimately we get this. And here electron cancels, and here EH. And we know that the electric field is equal to the voltage separated by the distance between the plates. Now this is VH by, here the distance between the plates, let's just say the plates here is the separation of positive charge and negative charge separated by the distance of the breadth of this rectangular conductor. So it is breadth equals to BV. Now BH is equals to B. So what is velocity? Well, here the velocity of these electrons are actually the drift velocity. And here we know that the current is equals to Vdena, VDENA, and here A is the cross-sectional area of this rectangular conductor, which is breadth into thickness. So from here we get Vd is equals to I by Na, so I'll write it nicely, NEA. So this is I by NE, and here the area we can just write breadth into time, thickness. This is by breadth cancels, therefore the voltage is equals to Bi by NET, or simply by net. Now this is the Hall effect, and also you can have something known as this RH, which is known as the Hall coefficient, which equals to 1 by NE. And also this is also equals to, I forgot to mention, EH by BJ. I had to look, sorry. So this is equals to the Hall field by B into J, where J is the current density. So basically it is just I by A, this is G. Now time for the Hall probe. And in Hall probe you will have more explanations rather than derivations. Now here, let's say that this Hall element, this is known as a Hall element, which is made up of some semiconductor, so it can produce a nice amount of potential difference, is placed between a magnetic field, or is placed in a magnetic field, and this is known as amplifier, which amplifies the strength of the potential difference, because the actual potential difference produced in this Hall element will be very small, and we need to amplify it to read it properly. And here, we we have to change and turn the position of the Hall element until we get a max potential difference. Well, the turning of this is explained by equilibrium. So we get max potential difference when, well, the electric force is equals to the Lorentz force, or they are in equilibrium, and we get max potential difference. Then what we do is read the voltmeter. We read the voltmeter reading to find out the max potential difference and divide by the factor that we have amplified, of course. And here, this is another figure which is of the same Hall element, in which a battery is supplied to produce current and electric field to separate the positive and negative charges for this Hall element right here. And from A to B, there is a whole voltmeter applied, and well, this U shape implies that the wire CD and AB do not intersect each other. And here you will have V H is equals to D I net. And oh, I forgot to mention the most important part. Hall probe, or you can also write Hall sensor, is a device which is used to measure, well, the value of magnetic field, or also known as the flux density of the magnetic field, which just means the magnitude of the magnetic field. And from here you have VH is equals to B, and current will be the same. The number of the electrons per unit volume will be the same. Is N equals to N by V, where N is the total number of electrons and T is the thickness. Well, these all are constants, so Vh is direct proportional to the magnetic field, which implies the more magnetic field we apply, that means the more potential difference we will experience, or sorry, the Hall element will experience. And this is it for today. If you learned something new, please like and subscribe. Thank you.